All right, so let's say here we're asked to find the most general antiderivative for all these functions below, all right? Now look, what I always tell people is this: antiderivatives are remarkably straightforward because what happens is they're just confusing at first because they're precisely the opposite of what you've been doing the entire time, okay? So we know that to find a derivative, we know how to do that, don't we? Like, look. Here, give me a second. Don't do anything. Just watch. You're smart. So let's say if I had y equals x to the third. How would you find its derivative? You're like, oh, it's easy. It's just 3x squared, right? The 3 swings out front. The x cubed has 1 taken away from it. It becomes x squared. Great. Ready? What if I didn't tell you that was x cubed? And I said, what function has a derivative of 3x squared? If you investigated for a little bit and thought it through, you'd probably get there. But the technique is actually kind of simple. It is just the opposite of what a derivative is. Let me uncover that real fast. I know that x cubed, what happens is the 3 swings out front, it multiplies the effectively 1 in front of the x, and then I take 1 away from the exponent. So I'm going to repeat what I just said. What I do is 2 operations back to back. I multiply the 3 by the number, and then I subtract 1. So I do multiplication and subtraction, right? So now I'm going to do the polar opposite. Now bear in mind, the opposite of multiplication is division, and the opposite of addition is subtraction is addition, right? But actually, I'm going to go totally opposite. Let me write this down because I realize it sounds a little weird. What I said I do first in derivatives is I multiply, and then I do what? Subtract, right? I multiply, and then I subtract. So just do the opposite. But it's not divide then add. Actually, it's add then divide. So let's go here. The 3 just comes along for the ride. Ignore constants. Take the x and add 1 to the exponent. 2 plus 1 gives us 3. We then divide by that newfound exponent, which is going to be 3. Incidentally, those 3's will cancel, and that gives us x cubed. Now there's a weird little rule here which says what you're supposed to do is you're also supposed to effectively add some constant c. Because like this could over here, could have been x cubed plus 1, x cubed plus 7, x cubed minus pi. Who knows? And that number would have gone away. So we kind of have a similar thing going here where we just go, look, I don't know what's going on here. So that constant, who knows if it was there or not. And so we can basically add that in. So watch. Let's do the exact same thing here. But now I am going to write this as what? X cubed plus, square root, who needs that? X to the 1/2 minus 5. So let's see what my antiderivative is, okay? Well, let's see, for x cubed, we know we're going to do what? We're going to add 1 to the exponent and divide by our newfound exponent. So it's going to be x to the 4th over 4. Plus, let's take the x to the 1/2 and add 1 to it. Well, that's going to give us x to the what? Well, 1/2 plus 2/2 gives us 3/2. You got to kind of go to the side, do that, no big deal. And now I'm going to divide that by 3/2. Let's be careful here. The 5, don't call it 0. A lot of people do that, and I understand why, because the derivative of 5 is going to be 0, but that's not correct here. What's this going to be? This is going to be 5x. Remember, the antiderivative of a constant is found by just slapping a letter in front of it. So remember, negative 5 becomes actually negative 5x. And now I'm going to make this look a little bit nicer, if I may. So that's going to be just x to the 4th over 4 that hasn't moved at all. But this is going to be, of course, plus what? I'll do it 2/3 times x to the 3/2 minus 5x, come on, plus c. You have to have that obligatory plus c there because you don't know what the constant was. All right, so you have a little bit of that kind of floating around. All right, so let's go ahead and try some other ones. Now again though, hopefully you get the technique. That is, oh, we're trying to find a function whose derivative is the thing that we are starting off with. So it is a little bit of a reversal of what we're used to. Also, I should point this out. Let's say that you think that's the answer. You think the thing you put in the box is the answer. Congratulations. Take its derivative. Barring some silly shit, taking its derivative should get you this. And if that's the case, then you know you have the answer. All right? So let's look right here. Let's say we got g of y is e to the 3y plus 2 over y plus 1 all over 1 plus x squared. Hold on a second. It's a little confusing, but if you think it through, you'll get it. Look, if I just gave you e to the 3y and said take its derivative, what would it be? Now again, that can be e to the 3x, e to the 3m. I'm just making up y for fun. So that's going to be e to the 3y, right? The derivative of e to the anything is e to the anything times the derivative of the anything, right? So what do you think it is if you do the antiderivative? It's really, really, really close. It's still going to be the e to the anything, but instead of multiplying by the derivative of the anything, we divide by the derivative of the anything. Okay, so instead of being e to the 3y times 3, it's just e to the 3y over 3. And if you don't believe me, if you think that's kind of weird, go ahead and try to take the derivative of what you get, and you'll find you will land right back here. If you do what I said, I promise you. All right, so let's go here and say we get ourselves e to the 3y, right? Rewrite what's in front of your face, but then we divide by the derivative of the anything, which is going to be 3. Now, hold on a second. What is 2 over y? Now, listen, don't do this. Let me show you the side real fast. Some folks do that, and that's understandable. So what they do is they go, John, got it. I'm going to add 1 to the exponent, make that effectively 2y to the 0, and then divide by my newfound exponent. Wait, shit. What you're supposed to do actually is this. You're supposed to recognize that 1 over x, or whatever, 2 over x, doesn't matter, is a special case. What's that special case? That's my natural log. You see, it's only the natural log of something that is found, whose derivative is found as 1 over the something. The natural log of x, its derivative is 1 over x. The natural log of 2x is 1 over 2x times the derivative of the inside, yes? So this is going to be, think of this as 2, right? 2 times 1 over x. So it's 2 times the ln of the x, yes? Now, that should be clear. It's not really x, it's y, isn't it? And there is this weird thing that I wouldn't sweat, but just do it to be smart. Mathematicians love when you slap on an absolute value around the y. Just makes them happy, okay? Reason being, we know that the y value can't be negative, so we have to give some love to that, okay? So now take a look. If you take the derivative of 2 ln of y, what do you get? I promise you get 2 over y, okay? Finally, plus, we have to play the game where things start to look recognizable, where something looks like a derivative that we happen to know. So we should know that the derivative of some function is, by its very definition, 1 all over 1 plus x squared. What is that something? That something is arctangent of x, or inverse tangent of x. That's tricky, but if you know your inverse trig derivatives, that'll work. And so we get a good old plus c. And that right there is our most general antiderivative, guys. Our most general antiderivative of the function given there. All right? So, let's try this one real fast. What if we've got y equals negative cosine of x plus secant x tangent x? Now, here's where we're going to be clever about this, okay? So what is our most general antiderivative? This, especially with trig, is where I really strongly encourage you to get your answer and then truly go backwards with your answer. So look, most folks recognize, they say, I know the derivative of the sine is the cosine. So for cosine of x, I'm going to go here, I'm just going to write sine of x, right? And you'd be partway correct. But if you, hold on a second, this thing's wigging out. Come on, give it a second. Sorry guys, it's just going nuts. There we go. Okay, so you think the answer is sine of x. But if you take the derivative of sine of x, you don't get that thing there, do you? No, but you're so close, aren't you? Like the derivative of sine isn't negative cosine. Oh, the derivative of negative sine is negative cosine, right? So always try to write the thing you think the answer is, but then go and double back and see if it lines up, okay? Plus, in a similar sense, is there a function whose derivative you know is secant x tangent x? I'm like, oh yeah, it's just good old secant x, right? The derivative of secant x is secant tangent, and then plus c, and now we're good. That's it. So again, antiderivatives aren't that hard. At first, they're going to feel a little bit quirky, but if you just go through the motions of doing the exact opposite of what you did to take the derivative, you'll get there quickly, I believe.